Hello. So this is our third video, and today I picked a question from May 2010, higher level, time zone 1, paper 1. Alright? So it's a question on our probability. It says, a continuous random variable x has probability density function where f of x is equal to 0 if x is less than 0, and f of x is equal to a times e to the power of negative ax if x is greater to or equal to 0. Okay? And what we also know is that the probability of x being less than 1 is 1 minus 1 over square root of 2. So the first question is a show that question, which is actually longer than what we would expect of a show that question. It's 6 marks. So let's take a look, right? So there are several things we got to remember before we can do any probability question. First of all, this is a question where the probability distribution is continuous, right? That's why we use a function like this to represent it, all right? So let me use the upper part of the board. Sorry. So let me copy it down. So basically, if we take a look at the probability, right? So let's say continuous random variable. Okay. And then let's copy the question f of x. Okay. A e negative a of x, where x is greater than equal to 0. Okay. If you take a look at this and you really try to sketch it, what it really looks like is this, right? 0 is here, x is here. It means that it doesn't have anything until x is greater than equal to 0. Okay. Notice that it's an exponential function, which means that no matter what a is, right, the distribution is going to look something like this, right? So that's the reverse of our distribution, right? So this is our f of x. So the probability of x less than 1 is 1 over, okay, this is our information. X less than 1 is 1 over this, right? So on the graph, what it means is that the area from 0 to 1 is going to be this. It means that we're trying to, okay, let's say 1 is here, okay? It means that this area, okay, area is 1 minus square root of 1, square root of 2, right? Remember that the area of any continuous random variable, the area under the distribution, it will be 1, which is to say that no matter, it's just to say that all of the total space of your distribution is 100%, which is 1, right? So that makes sense. Alright, so now that we have a better picture of what it looks like, we can actually try to solve this question, right? Basically, it tests you the knowledge of the fact that the area under the distribution function represents the probability. Okay, so this is not in your data booklet. It doesn't go through the it doesn't give you this fact. It only gives you variance and mean. It doesn't give you the probability itself. So you got to know that area under the distribution is whatever the probability between x1 and x2 is, right? In our case, let's say x1 is 0, x2 is 1, which is to say between 0 and 1 happening, probability is the integration, the integral of the function there, right? So let me put this into a better, okay, let me adjust this a little bit, okay, very nice. So now what we have is we got to show, okay, so probability of x less than 1 really is just the probability between x between 0 and 1, right? Because if it's less than 0, the probability is 0. Okay, and this is gonna be, right? So the lower bound is r0, upper bound is 1, and our function, which is ae negative ax dx, right? So this is our is how we find the probability between 0 and 1 for this particular distribution. And we also know that the value of this is equal to 1 minus 1 over square root of 2. Okay, so let's try to integrate this first. Okay, how are we going to do this? We can pull the constant a out, right? And then what we can do is integrate a to the power of negative ax, which is, okay, the reciprocal of that, e to the power of negative ax, okay? And this whole thing from 0 to 1, right? So that in fact is just equal to negative e to the power of negative ax from 0 to 1. All right? That's cool. The next step is, of course, to find a, right? So this is equal to negative a, right? Plugging x equals to 1 over here, and subtract, all right, negative e to the power of 0, right? And that, of course, is negative e to the power of negative a plus, this is just 1, okay? And this is supposed to be equal to what is given in our question, which is 1 minus 1 over square root of 2, right? This is given, okay? So I don't know why I'm doing this, but let me just write it. It's given, right? So therefore, what do we know? We know that, therefore, the 1's cancel out, and the negative cancel out. So e to the power of negative a is equal to square root of 2 negative 1, let's say, right? So we can say that a, which is 2 to the power of negative 1/2, all right? So we can say we take ln on both sides, and we get negative a equals to ln of 2 of negative 1/2, which is, of course, using our power law, we have this. Okay, we move the negative 1/2 outside over here. We get negative a equals to negative 1/2 ln of 2. So therefore, finally, a is equal to 1/2 ln of 2, right? So that's our solution. Let me circle it and give it a sign. Okay, so this is our 6-mark question, right? So you got to remember that the area under your distribution function will be the probability, and that's how you can quickly find the integral of the function and then solve for a. Then let's take a look at something which is in your oh no, it's also not in your data booklet. All right, the next question, let's go back and take a look. Okay, I'll remove this. Next question says find the median of x. All right, so find the median of x. This is a question which again tests you the knowledge of your probability distribution function, right? What does the median mean? Median is the 50 percentile of the function, right? This is not to scale, but let me redraw something that might be a little bit more accurate. So let's say the probability distribution of our function, still it's this exponential graph, right? This is our f of x, and this is our x, right? And then the median would be the point where 50% of the population is bigger than that point and 50% is smaller. So let me use, let's just say, I would say the median would be somewhere here. And then if we mark if we mark it with this line, we could say that, suppose we got 2 area, right? And then this is probability x smaller than medium, right? And then we got another half, which is probability, which is this part. Okay, this is probability x bigger than medium, right? It would mean that, let's say this is A, and this is B. It would mean A equals to B. Okay, if it's a median, right? If it's actually the median, then A will be equal to B, which is to say that you have half of the chance to be smaller than the median, half of the chance to be bigger than the median. Okay, so that's the idea of the median. And if you know that, then it would mean what? It would mean that to find the median, okay, let's say median, okay, let median equal to m. Okay, so our median is this point m. It means that the integral of this thing and f of x dx would be the same as the integral of your from median to infinity, really, of f of x dx. All right, and that it would be just 1/2. Okay, no matter which side you're at. I think that's pretty straightforward. Okay, so we work on this part because we don't want to work with the infinity at this point yet. So basically we have 0 to m of our probability function dx should be 1/2, right, by the definition. And we already did the integral, but we could do it again. Basically it's a times 0 to m e negative ax dx should be 1/2, which is to say a times, and then you do reciprocal e ax from 0 to m is 1/2. Oh, sorry. Let me move this up a little bit. Okay, right, which is to say negative e negative ax from 0 to m should be 1/2. And then we plug in m, right? Negative e negative a we know the value of, and then plus plugging in 0. Okay, so we have negative e plugging m equals to x equals to m negative am plus, when x is equal to 0, e to the power of 0 is just 1, so minus 1, it's just 1, should be 1/2, which is to say that e to the power of negative am is equal to negative 1/2, right? All right. So we could sorry, this is, I'm missing a negative, that's why it's looking a bit weird. So e to the power of negative am is just equal to 1/2, and then we take logarithm on both sides, right? We take logarithm on both sides, we get what do we get? We get negative am is equal to ln of 2 to the negative 1, which is negative ln 2. So m is equal to ln 2 divided by a. Okay, and recall what our a is. Our a is 1/2 ln 2, right? Which is to say, I don't need the arrow. So we know that m would be in the end equal to 2. Okay, so therefore median is 2. Okay, which is to say, in our particular example, when we take a look at, okay, when m is equal to 2, when it's 2 here, the area before 0, from 0 to 2 would be 1/2, and the area from 2 to the other half would be 1/2, would be 50-50. All right. Okay, so we should keep this sheet because I kind of like it. Anyway, it's pretty neat. Okay, let's go back to the third example, right? Calculate the probability that x is less than 3 given that x is greater than 1. Right? So if you look at this question, if you see given in any question, you should immediately think, it's a question on conditional probability, right? So recall, now this one you're lucky, you do have a a formula from your data booklet. I'm just getting my paper out. That's why the screen is not showing any change. Anyway, so in your data booklet, let's say data booklet, it's SL 4.6 of your data booklet, which gives you conditional probability. Okay. Okay, and then recall that the formula for doing conditional probability is this. Okay, probability of A given that B has occurred is the probability of A and B divided by probability of B, right? Let's review this a little bit. So if you remember what this means, let's say we have a Venn diagram, right? Probability of A is this, probability of B could be this. In essence, probability that you would get an A, given that you know it's part of B, is really this area, right? This is probability of A and B, right? This is what the question is actually, the area that it's looking for. But it's also restricted. It's going to be bigger than just this area itself, because we also know we already eliminated a bunch of the outer spaces, right? We eliminated all these parts, which is to say that we know that it's given that it's B to start with, then we just have to calculate this area relative to the whole area of B, right? So this is our conditional probability. Now, let's translate this language into conditional probability, right? So given that x is bigger than 1, find the probability that x is less than 3, which is to say we're looking for what? Probability that x is, what is it? Smaller than 3, isn't it? Smaller than 3, given that x is bigger than 1, then in essence, we're looking at something that's between, let's just write it down, that x is bigger than 1 and x is smaller than 3, right? This is what our translation goes to, given that probability of x bigger than 1, right? So this is how we're supposed to write this. And then the top part, okay, if it's bigger than 1 and it's smaller than 3, right, we're essentially looking at probability between 1 and 3 over probability of x greater than 1, right? So if we go back to our probability distribution, it looks something like this. It says that, let's say 1 is here, and then we know that 2 is the median, isn't it? So 2 is the median, and okay, maybe 3 is here. And so given that it's somewhere bigger than 1, right, we are looking for the area from here to here relative to the red area. Okay, so let me do this whole thing. The red area is this. Okay, so we're really looking for, let's say, red area, let's give it, okay, is x bigger than 1, and then this area is between 1 and 3, right? So we're looking for the fact that we're looking for the area of this one given that it's in the red. So I should not have used this. We should have reversed it. But basically, you know what I mean, right? In this case, we're looking for area of the blue part relative to the white part. Here we're looking at the area of the blue part relative to the red part. Okay, so it's the same idea. Okay, and now what do we have? We what have we got? Do we have any information which we could just continue to use from above? Okay, so what do we have that we could use? Damn it. So first of all, we only have probability of, okay, so we know, so this is given. Okay, we do know probability of x less than 1, which is our 1 minus square root of 2. This is given in the question, and so we have to say that this area is 1 minus square root of 2, which is probability of x less than 1, right? And so to find the red area, we have to use the knowledge that the whole area adds up to 1, right? So given that probability of x less than 1 is this, probability of x bigger than 1 would be 1 minus probability of x smaller than 1, right? Because the white area and the red areas, the region should add up to 1. So 1 minus this, which is 1 minus square root of 2. Okay, and this is just 1 square root of 2. Okay, so this is one thing we know. And what else do we need to know? What we also need to, so now we are only left with the top part, which is, the numerator, probability between 1 and 3. So probability between 1 and 3, obviously, would just be 1 and 3 and e negative ax dx, right? I think we did this already, right? So it would come up to be negative e negative ax from 1 to 3, right? So it's going to be negative e negative 3a plus e negative 1 negative 1a, okay? So if we do the math, it should be something like this, okay? So then should we just plug in our a, maybe? So remember, our a is our 1/2 ln 2, if I remember correctly, which is really ln of 2 square root of 2, right? So it's really negative e negative 3a, okay? So negative 3 ln 2 square root of 2 plus e of negative ln 2 square root of 2. So if we want to be very sophisticated and everything, ln 2 negative 3 over 2, right? This is by power rules. Okay, so we move the negative 3 over here, plus e of ln 2 negative 1/2, right? And of course, power rule dictates that this e to the ln whatever would be cancelled out, which is just negative 2, 3 plus 2, 1/2. Okay, this is not done yet because we have to divide the whole thing by our what's on top, right? Sorry, we have to divide the whole thing by this. Okay, can we just write it on the same piece of paper? I suppose so. So basically, what we have is this, right? So so we have two things we know. We have this and that, and so probability of x smaller than 3 given that x greater than 1 is -2 -3/2 plus 2 -1/2 divided by, let's like carve out a space for our lovely calculation. Okay, divide by 1/1 square root of 2, which is to say it's square root of 2 times okay, so this is gonna be, okay, let me rewrite this, plus, right, I suppose. So basically these cancel out. Okay, so it's gonna end up being, oh, I forgot the negative over here, -1 square root of 2 squared plus 1, which is just 1/2. Okay, that's it. So that's our third question. Okay, there's something I do want to mention, which is completely extra and not related, not in your syllabus. So let me just write down our solution. So we've done this, we've done that. Medium is 2, and probability that x is less than 3, given that x is bigger than 1, is gonna be 1/2, right? So what we've learned is that this blue area divided by this red area should give you 1/2, right? Now let's do something special, which is out of your syllabus, but it actually is quite interesting. So as we know, let me copy this again. Function is 0 a e -ax x is 1 x greater than 0. Okay, so let me copy this. So this kind of distribution is, not surprisingly, exponential distribution, right? It doesn't matter what our a is. In the general shape, it's gonna be something that looks like this. All right, that's our exponential distribution. Now there's an interesting property, which is called the memoryless property of exponential distribution. So let me write this. Memoryless property of exponential distribution. Okay, this is not in the syllabus, so you don't have to worry about this, but it's just gonna help you figure out question C a little bit faster, right? So what does this memoryless property say? It says that basically the history of what happened doesn't really matter. Only what is going on right now really matters. Okay, so let's use an example, right? Suppose that we set an alarm, right? And we know that the alarm has not sounded in the past 10 seconds. Okay, and we know that the probability of this alarm sounding is follows an exponential distribution. Okay, so if we know that in the past 10 seconds the alarm has not sounded, then what is the probability that it's going to sound within the next 2 seconds, right? And really what the question is, this kind of question, if we use conditional probability, we can translate it as this: probability of alarm sounding at time t, where t is within 2 seconds after the 10 seconds, given that it has not sounded in the previous 10 seconds. So given that the time is it's going to sound sometime after the 10th second, right? Basically what the question really is doing is this: given that it's after after 10 seconds, what's the probability that it's going to sound within 2 seconds after the 10 seconds, okay? And if we're gonna do our typical conditional probability, you're gonna follow it as usual, right? It's gonna be given that the probability, this is t greater than 10, and this is probability that it's t is less than or equal to 10 plus 2, and okay, let's do a big and and it's t greater than or equal to 10, right? Right, so let's say, let me remind you what my question is. Given that probability of an alarm sounding follows an exponential distribution, and given that it has not sounded in the past 10 seconds, find the probability that it sounds within the next 2 seconds. Okay, so this is the question setup, right? So the probability of an alarm sounding, it follows an exponential distribution. It doesn't matter what our A is at this point, it's just that it follows this general distribution. Given that it hasn't sounded in the past 10 seconds, what's the probability that it's gonna sound in the next 2 seconds, right? And then if we write the standard form, the probability should be something like this. And now, of course, if it's gonna be if it's between if it's bigger than 10 and smaller than 10 plus 2, we can really just write probability of t between 10 plus 2, probability that it's greater than 10, right? So it looks awfully like our question. Our question says what was our question? Let's take a look. Right, our question, we're trying to look for between 1 and 3 and x greater than 1, right? And then by this point you should actually go through whatever your calculation is, right? You're gonna have right, no matter what your A is, you're gonna have this between 10 and 12. Let's say this is 12, that this is 10 plus 2, which is 12, right? And then whatever your A is, okay, so this is what your top you're gonna get, divided by greater than or equal to 10. So in the end, you're really just doing 10 to infinity by the same function, right? Okay, so this is the idea, right? Now, what the memoryless property says really is that it doesn't really matter the fact that it's not sounded in the past 10 seconds. So the memoryless property, the memoryless property of exponential distribution says that, well, we don't really mind if it's not sounded in the past 8 seconds, or if it's not sounded in the past 50 seconds. If you only want to know what's the probability that it's going to sound within the next 2 seconds, then you really just have to find the probability of it sounding in the 2-second interval. All right, so by the memoryless property, we can really just say that this is going to be equal to the probability that it's gonna be between it's going to sound in the 2 seconds interval. Right? Let me think. Yeah. Alright, so we can try to calculate this, but we don't have to do that. We don't have to prove this. But what it essentially is saying that it doesn't matter what happened previously. Alright? So based on that fact, what we could see, okay, so if we translate this into our diagram, basically it's saying that, you know, in our case, let's say this is 10 seconds that it happened. It doesn't matter, right? The distribution after that 10 seconds, it's going to be exactly the same. So it's not going to change. So we don't have to care about what happened, whether this x is 10 or 50 or whatever. If we're just looking for a specific time, let's say, basically in our example, we're trying to look at 2, right? So it's going to be the same as going from 0 to 2. Okay, so it's saying that by our property, memoryless, it's saying that this area is exactly the same as this area. Okay, it looks like this. All right. And in fact, we can do a quick proof of that. We can use this particular example, but we could actually go through a quick proof, right? So actually, we can just use this example, right? So before, we already have the general negative a ex dx. Let's just do this first, because then it's gonna be much faster, right? So the general integral of this is this, right? So in this example, let's say within 2 seconds after it has not sounded by the first 10 seconds, right? You're gonna have between 12 and 10, and then so this is essentially negative e negative ax from 10 to 12, right? And this is the general integral, right? E negative a to x. All right. Well, we haven't learned this yet, but this is integration from till infinity. But it's really the same kind of logic where you do integration from infinity minus integration from 0 to 10. So in the end, you will get this. Just trust me on this for now. And what will we get above? Okay, so we're gonna get we don't have much space. Negative e negative 12a plus e negative 10a, right? And here, sorry, this should be 10 to infinity. Okay. The first one is going to tend to 0 if you plug in the infinity. So you're going to have 0 minus negative e to the negative a x, where x is 10. So you're going to have positive here. You're going to have e to the negative 10a, right? And so we got basically this part is just 1. Okay, so let me write 1 on left hand side, and the next part is what? Negative, now this is interesting, negative 12a divided by e to the negative 10a, right? So what are we gonna get? We're gonna get 1 minus e to the negative 12a plus negative 2, right? Negative 2a. So what is this equation saying, right? It says that, what does this area represent? Well, first of all, we recognize that when x is equal to 2, that's where you go from, this is really from negative e negative ax, where you go from 0 to 2, right? If you want to verify that, because negative e negative ax from 0 to 2 is going to be negative e negative 2a plus 1, right? So this is exactly what it is. And what does this represent? It represents probability going from 0 to 2 in our case, right? So that's pretty cool, really, because this is really what this diagram is saying, right? It says that, well, it doesn't matter if you're doing, it doesn't matter what this x is, right? In the end, if we want to know what's going to happen within 2 seconds, we just have to know what's the general case of happening from 0 to 2. So it doesn't really matter, right? You could, if you're, it doesn't matter if you're asking when will the alarm, okay, probability of the alarm sounding, if we know it didn't sound in the first 500 seconds or in the first 10 seconds, it doesn't matter. The key thing is what the change in x is, right? We want to know within the 2-second interval, right? So we've in fact shown that, yeah, it doesn't matter what it is. It really is just the same as probability, right? If you take a look at this, between 0, t, and 2. Okay? So this is what our diagram has been trying to do, right? So that's kind of cool. So, yes. So using the and so the only continuous random variable that has this memoryless property is the exponential distribution. So going back to our diagram, okay, going back to our problem, this is an exponential distribution, right? And it's saying that, okay, given that the probability, okay, x is 1 is maybe here, 2 is here, this is the median, right? Median. And then 3 is here. So we're looking for the probability of x less than 3, given that it's bigger than 1. So we're looking for the blue area. This is calculate probability that x is less than 3, given that x is bigger than 1, right? Did I draw the wrong thing in the front? Given that x is less than, oh, sorry, yeah, I'm drawing the wrong thing here. Forgive me, I shouldn't be using this tiny paper. Let's just use a paper we have, right? So we're looking at, given that it's less than, x is bigger than 1, which is the red part, what is probability that it's between 1 and 3? Well, now, in fact, because we are looking at the memoryless property of exponential function, it doesn't matter that that it's given that it's bigger than 1. Okay, what we can do instead is to translate this into the change, right? So if you use the alarm example, what this really means is that find the probability that the alarm will sound in the next 2 seconds, given that it has not sounded in the first 3 seconds, right? So if you think about this, if you take a look at this problem here, it means that if we translate this, given that it's not sounded, okay, before 1 second, Okay, given that it has not sounded before 1 second, what's the probability that it will sound? It will sound in the next 2 seconds, right? And obviously we got the 2 is 3 minus 1, right? Given that it has not sounded in the past 1 second, what's the probability that it will sound in the next 2 seconds? And so instead of doing the whole calculation, you could just go, you could just really just find, this question is really asking you probability of x less than 2. It's really asking for this, right? Based on our memoryless property of exponential distribution, right? And now we're super lucky because we already found the median. The median is 2, which is to say that there is a probability of 0.5 of being less than 2. And this is just 1/2 because 2 is median. Okay? So that's kind of cool, right? So if we know what the memoryless property of an exponential function is, we could figure this out pretty quickly. And because, as I said, the only continuous random variable which has the memoryless property is the exponential distribution. If we know that a continuous random variable which is memoryless, we know that it must be exponential. So sometimes that could come in handy if you're trying to do this question, right? But I think the memoryless property is very useful, right? So let's just go back again, right? Right? It just says that it doesn't matter what the x is. The area here is gonna be the same as the area here, given that the interval is the same. All right. So it doesn't matter that it has not sounded. It has not sounded before 1 second. It doesn't matter. What it's really asking is what's the probability that this alarm will sound within the next 2 seconds, right? And so you find it really is saying that. So based on the exponential, it's really saying that this area here is the same as this area here. Okay. Not exactly like that. You gotta do the nicer curve like this, right? So that makes it more pretty. Okay, forget about the diagram. I think this is the better diagram. Okay, the idea is that if you know that exponential distributions are memoryless, then you could apply that property and simply figure it out in 2 seconds. But I think most of us don't need to know that, so that's fine. So we can solve this problem very quickly. So yeah, so that's our continuous random variable. I really think that this is a part that is the easiest and the most difficult because it combines your knowledge of your of probability distribution, but it also uses integration technique. So it depends on how evil they are. They could make the function itself very complicated, very difficult to integrate. And you also have to remember a bunch of the functions. So you got to remember that it's the median is the point that's 50-50 before and after. And you also have to remember that the total area under the probability curve is 1, right? So that's the idea. But once you know that, I think it's really, you get the probability you get the probability part out of the way very quickly, and you just have to deal with integration. And for some of the people, I think integration is a very mechanical process where it doesn't require much of any thinking. So it depends on the person, really. I think to me this is the least fun kind of question, because everything is quite technical at this point, but it's also the most difficult because it comes at the very end of your it's supposed to come at the very end of your syllabus because it combines a lot of things. Alright, so that's it for today. I hope you're all good. Bye bye.